Hey everyone, and welcome to this explainer. So look around you. The mountains, the deep valleys, those massive sweeping plains, they look pretty permanent, right? Like they've just always been there. But actually, the truth is that the Earth's surface is this incredibly dynamic, constantly changing canvas. It's actively being sculpted literally right this very second by some massive forces, both deep underground and right here on the surface. Today, we're going to create a high-level visualization of exactly how the shaping of the Earth's surface happens. Let's get into it. So here is our blueprint for how a planet gets sculpted from the inside out. We're going to start with Earth's continuous transformation, then look at internal plate tectonics, weathering, and erosion. After that, we'll dive into the agents of gradation, and finally, wrap up with the human impact. All right, part 1. Earth is always changing, the continuous transformation. Moving right along to part 2, internal forces, plate tectonics, the inside sculptor. Okay, to really understand our planet, you kind of have to accept one fundamental truth. Every single geographic feature you have ever seen is just a temporary result of millions of years of continuous forces battling it out over the landscape. You see, the Earth's outermost layer isn't just one solid shell. It's actually broken up into these massive puzzle pieces called tectonic plates, and they are constantly surfing over a super hot, semi-molten layer called the mantle. So visualize it like this. You've got internal forces and external forces. Those internal tectonic forces, those are the ones triggering earthquakes and building volcanoes. And the way these giant plates interact at their edges, their boundaries, well, that dictates exactly what kind of landform is going to get pushed up to the surface. So how do these boundaries actually build the world around us? Well, imagine two plates colliding head-on at a convergent boundary. The Earth literally crumples upwards, forming massive fold mountains like the Himalayas. And fun fact, because that collision is still happening right now, the Himalayas are actually still growing about an inch every single year. Now, if it's an ocean plate hitting a continental plate, the ocean plate sinks, and that causes deep earthquakes and volcanoes. Then we have divergent boundaries. This is where plates pull apart from each other, which allows magma to rise up and create brand new crust. The Mid-Atlantic Ridge is a perfect example of this. And finally, transform boundaries. This is where plates stubbornly slide past one another, building up massive tension until snap. They shift, causing severe earthquakes like we see at the San Andreas Fault. And the engine driving this whole shebang, convection currents. Intense heat from the Earth's core boils the mantle, driving this nonstop movement. Which brings us to part 3, weathering, breaking the rocks, the outside chisels. Now we pivot to weathering. And I really want to emphasize a crucial definition here. Weathering is the process by which rocks break down into smaller pieces on the Earth's surface, absolutely without movement. It is exclusively about the breaking of the rock. Literally, zero transportation is involved here. So when you see a rock with deep cracking and splitting, you're seeing something that happened right there in place. It's a remarkably slow, continuous process that preps the rocks for the next destructive phase, but at this stage, those broken pieces haven't gone anywhere at all. There are 3 main ways this breakdown happens. First, physical weathering. This involves structural forces, like extreme temperature changes making a rock expand and contract, or water freezing inside cracks and expanding like a wedge. Second, chemical weathering. This happens when minerals in the rock react with water, air, or acids in the rain, which literally changes the rock's chemical composition. And finally, biological weathering, which is entirely driven by living things. Actually, let's zoom in on biological weathering for a second because it's pretty mind-blowing. Think about how something as seemingly harmless as a little tree root can seek out a microscopic crack in a solid stone, grow, expand, and exert enough pressure over time to physically split a massive boulder right in half. No way, right? But it happens. Even burrowing animals or tiny microscopic organisms producing localized acids actively contribute to breaking down the Earth's crust. Nature is just relentless. All right, part 4, erosion. Moving the pieces, the transporters. If there is one big aha moment you take away from this entire explainer, let it be this clear distinction right here. Weathering only breaks down the rocks. Erosion wears away and transports the material. Erosion is all about movement. Basically, weathering breaks it, erosion takes it. You can think of it as a really straightforward visual equation. On one side, we have the rock breaking down in place. That's your weathering. On the other side, we introduce wind, water, ice, and gravity. They swoop in, scoop up those loosened fragments, and carry them away. Boom! That is erosion. And nature uses four major transporters to move this stuff around. We have coastal erosion, where sea waves relentlessly pound and wear away the shoreline. There's water erosion from rivers and rain, which is incredibly powerful. Wind erosion, which totally dominates in dry, sandy environments like deserts. And glacial erosion, where massive, super slow-moving rivers of ice just scrape up and carry away everything in their path.
On to part 5, the agents of gradation, leveling the Earth.
So when you combine these external forces, the weathering, the erosion, and the eventual dropping off or deposition of all that material, you get what geologists call gradation. It's this grand, sweeping process of leveling the Earth's surface over time. There are 5 main agents of gradation working 24/7, 365 days a year to smooth out our planet: running water, glaciers, wind, sea waves, and groundwater. Let's take a look at exactly what kind of art they leave behind. The absolutely crucial point here is that each agent leaves a very specific, easily identifiable signature on the landscape. For example, running water cuts deep into the earth to form sharp, V-shaped valleys. Glaciers, on the other hand, they're huge and bulky, so they scrape out wide, U-shaped valleys. Wind builds our sand dunes. Sea waves carve out our coastal cliffs and drop off sediment to form beaches. And groundwater? Well, groundwater is sort of the secret agent working right below us. It dissolves soluble rock, like limestone through chemical weathering, to create these massive underground caves and sinkholes. Now, of all of these, running water is without a doubt the most dominant geomorphic agent on the planet. A river's erosive power depends entirely on its discharge and its velocity. Over thousands and thousands of years, it just slices right down through its bedrock, turning a small, tiny channel into a steep, V-shaped valley. And eventually, if you give it enough time, a magnificent canyon. And finally, part 6, living on a sculpted planet, the human impact. Because eventually, all of this macro-level tectonic and glacial activity trickles right down to the human scale. And the harsh reality is, erosion has a severe human cost. When water and wind strip away fertile topsoil, agricultural yields plummet, which directly threatens our global food supply. Heavy river and coastal erosion literally washes away land, homes, and critical roads. It destabilizes the ground beneath construction sites and mines, massively increasing safety risks. And it even hurts local economies by damaging the pristine beaches and rivers that tourism and fishing industries rely heavily on. But hey, we aren't helpless observers in all this. Humans have actually developed some incredibly clever conservation techniques to fight back and slow these natural erosive forces down. For instance, we use continuous contour trenching, that's digging trenches along the natural flowing curves of a hill to catch and hold rainwater so it actually soaks in, rather than just washing all the soil away. We build earth embunding, which are basically these small embankments that slow down surface water runoff. And we use terracing, which is literally cutting hillsides into level staircase-like steps to prevent catastrophic soil slip. By mapping out and really understanding how both the internal forces, like earthquakes, and the external forces, like erosion, operate, we can actually safely navigate a highly dynamic, unpredictable planet. It's exactly what allows us to manage our natural resources, protect our homes and settlements, and predict natural disasters well before they ever strike. And that brings us to the end of our explainer. You know, the Earth is shifting beneath our feet right now as we speak. Mountains are growing by millimeters, valleys are getting just a little bit deeper, and coastlines are constantly being redrawn. This sculpting is an unstoppable, ongoing event. So the next time you look out at a beautiful landscape, I want you to ask yourself, what forces built this? What forces are actively trying to tear it down? And how will it all shape the map of our future? Thanks so much for joining me today, and keep exploring.